Welcome to the 8th and final week of the course. This week we're going to go over several examples on protection in microgrids. We're going to see how protection takes place in grid-connected and islanded modes of operation, and how adaptive protection works. Later in the week, we're going to cover applications of DC and AC microgrids that have been implemented in several sites around the world. In this video, we will take a look at the sequence of actions that takes place in a grid-connected microgrid when a fault takes place at different locations, and we will look at the effect of having distributed generation, such as photovoltaic systems, in the microgrid. The medium and low voltage feeder and switchboard layout can be modeled, as shown in the figure. Two circuit breakers that are denoted as CB in the figure are connected at both sides of the medium voltage, low voltage transformer, and can be interconnected by a follow-me function. Through this function, when either of the circuit breakers fails to trip properly, the other interconnected circuit breaker trips as a backup. In this case, CB0 and CB1 have the highest delay in the microgrid, so they are the latest breakers to trip. The overcurrent relays, such as CB1.1 and CB1.2, located downstream, have a higher speed. In today's example, we will learn what sequence of actions takes place when a fault occurs at different locations in a grid-connected microgrid. Let us take a look at grid-connected microgrid layout. As shown in the figure, we have two feeders connected to the low voltage or LV bus and to the medium voltage or MV bus via a distribution transformer. Each feeder has two switchboards or SWB in the figure. The switchboards connect the various distributed generators and loads to the LV feeder. The circuit breakers are responsible for tripping and isolating the different areas, distributed generators, loads, and/or feeders during a fault. When fault F1 occurs, that is on the medium voltage feeder towards the grid side, then the microgrid is isolated as fast as 70 milliseconds. The challenging part of this case study is that the amount of fault current at CB1 can vary greatly. This is due to the fact that this fault currently is injected from the microgrid to the upstream network at CB1 and varies depending on the number and type of distributed generation units connected to it at each moment of the day. These electronically interfaced distributed generators may contribute up to 1.1 or up to 2 times of their rated current, whereas electrical machines in general, such as diesel engines, may generate a fault current up to 5 times of their rated value. This difference in fault current values may be too low for the fault current sensing of the circuit breakers, and hence blinding of protection when the circuit breaker fails to trip may occur. Therefore, this rather low fault current generated by the distributed generators can result in a sensitivity problem in the protection. A solution to prevent this would be to add additional control loops to the distributed generators to have them generate higher fault currents. An alternative solution to the sensitivity problem during faults at F1 is to have voltage sag sensing, where both the amount and duration of the voltage drop can be measured and analyzed during the fault. Let's see what happens if the fault occurs at F2. In this case, CB0 will immediately disconnect after sensing the high fault current provided by the upstream network. CB1 will open simultaneously by the follow-me function of CB0. If the fault occurs at F3, the largest portion of fault current is provided by the grid through CB1.1, CB1.2, CB2, and CB1 or CB0. The fault is cleared at the microgrid level, where the smallest possible portion is disconnected by CB1.1 and CB2.1 using the follow-me function. If CB1.2 fails to trip, then CB1.1 or CB2 will react as backup protection. If these breakers also fail, then the whole microgrid will be disconnected by CB0 or CB1. The sensitivity of CB1.1 may be disturbed if a large amount of electronically interfaced distributed generators is installed and switched on a SWB1 or switchboard 1, which may cause blinding of protection as discussed before. If a fault occurs at F4, then a high short circuit current is supplied to the fault location, both from the main grid and surrounding distributed generators. As a result, the fault can be cleared by tripping the CB2.4, which is generally a fuse. If CB2.4 does not trip, then CB2.5 reacts. In general, there is no sensitivity or selectivity problems for the fault at F4. To summarize, in this video we have seen how the protection occurs in a microgrid during the grid-connected mode and some of the challenges that may arise during faults. One of the main challenges discussed is the current sensitivity problem at the breaker CB1 that is usually caused when a large number of electronically interfaced distributed generators, such as small PV systems, is installed in the microgrid. In the next video, we will see an example on protection during islanded mode.